Hey guys, today I want to review with you Lewis dot structures in molecular geometry. It's a good idea to maybe take notes with me because I'm going to be going over some stuff that will show up on comps. So make sure you're paying attention. So the first thing we got to do before we can draw any sort of Lewis dot structure is we have to know where our valence electrons are on the periodic table. So you guys should know that this is one valence electron. This group has two valence electrons, 3, 4, 5, 6, 7, 8 valence electrons. Okay, so that's something you definitely need to know before you can start drawing a Lewis dot structure. So I'm going to go over a couple examples with you. The first example is CF4. CF4. So if I said, hey, draw the Lewis dot structure for CF4 and tell me its molecular geometry. First thing you have to do is tally up the valence electrons. Okay? So you have copper and you have fluorine. Carbon, my bad. Carbon has 4 valence electrons because it is in group 4A. Okay, so it has 4 valence electrons, and there's only one carbon, so that's it. Fluorine has 7 valence electrons, but you have 4 fluorines, so we're going to multiply it times 4 to give us 28. So that will be a total of 32 electrons. So a total of 32 valence electrons that we need to put in our Lewis dot structure. So what you have to do is take your singular atom, put it in the middle, so the one that there's only one of, which is carbon, and then you're going to put your 4 fluorines around it, connect them with bonds, okay, and then you need to fill up the octet of everything. And remember, octet means 8. Oct means 8. Like an octagon has 8 sides, an octet means you have 8 valence electrons around you. Okay. So now we filled up everything's octet. Let's see if we've used 32 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We did it. So we are done. So the two things you guys want to check are, have you used all 32? Yes. Does everything have an octet that needs it? Yes. So we are good. That's how you correctly draw a Lewis dot structure. Let's look at a second example. And it's going to deal with an exception to the octet rule. BH3. This is a really good example because it shows you 2 big exceptions to the octet rule. Okay, so first let's tally up our valence electrons. So we have boron and we have hydrogen. It's very important that you do this step and don't skip it because it can get you into trouble if you skip this step. So boron, if we look at the periodic table, boron has 3 valence electrons. And hydrogen has 1 valence electron. But I have 3 hydrogens. So let's multiply it by 3. So that gives me a total of 6 electrons I need in my picture. Okay, so I'm going to put boron in the middle with 3 hydrogens around it. I'm going to connect them with bonds. Okay, so I've already used all 6 of my electrons. And that is okay because both of these atoms are exceptions to the octet rule. Hydrogen only needs 2 valence electrons around it. It doesn't need an octet. So only needs 2. Only needs 2. And it has 2 because each line counts as 2 electrons. So it's happy the way it is. Doesn't need any more electrons around it. And boron only needs 6. And if you remember, we went over that in our notes. That group 3 elements are exceptions to the octet rule, and boron is the big one you'll see because I'm not going to give you any ionic compounds to draw on the comps. There's going to be covalent, and boron is your only nonmetal in group 3. So this one only needs 6. So that's it. So we've used all 6 valence electrons. Everything that needs an octet needs it. Nothing needs an octet. Hydrogen has 2, it's happy. Boron has 6, it's happy. So we're done. Okay. Let's look at our third example. Our third example is CO2. Okay, so let's tally up those valence electrons. So I have carbon and I have oxygen. Carbon has 4 valence electrons and oxygen has 6 valence electrons. Okay, carbon has 4, oxygen has 6. And I have 2 oxygens, so I need to multiply that times 2. 4 plus 12 is 16 electrons. Okay, so that's the total number of electrons I need in my picture. So I'm going to take my carbon and put it in the middle, and then put my 2 oxygens around it, and let's connect them with bonds. Okay, now I need to fill up everything's octet. Okay, did I use 16 electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I used 20 electrons. That's way too many. That's why it's important that you do this and don't skip this step. Because if you skip this step, you might just be like, oh, done, moving on with life. But you can't do that. You have too many electrons on here. So those ones can't be there and those ones can't be there. Now we have 16. The problem is with only 16 electrons, carbon doesn't have an octet. So what you have to do is you have to take 2 of them from somewhere and make them into a double bond. Okay, so you only need to make double bonds if you run out of electrons and something doesn't have an octet. So let's kind of redraw that to make it look nice. So I'd have double bond here, double bond here. Now let's see, did I use 16 electrons? 2, 4, 6, 8, 10, 12, 14, 16. Yes, I used 16 electrons, so that's good. And does everything have an octet? Yes, this has 8 things around it, this has 18 things around it, this has 8 things around it. So we are good. Okay, so that's when you form double bonds. All right, I've got 2 more examples for you. The next one I have is SF2. Okay, SF2. So we have sulfur, we have fluorine. Let's see how many valence electrons sulfur and fluorine have. Sulfur has 6 valence electrons, and fluorine has 7 valence electrons. Okay, and I have 2 fluorines, so let's double it. So 6 plus 14 is 20. Okay, so now we're going to put sulfur in the middle with the 2 fluorines around it. Okay, now let's fill up everything's octet. And let's see if we've used 20 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20. Okay, we used 20. Everything has an octet. We're good. So we can move on. Okay. Last one I'm going to show you is a polyatomic ion. It's NO3 minus. Okay, this is nitrate. So we have nitrogen, and we're going to do it basically the same way, and we have oxygen. Nitrogen has 5 valence electrons, oxygen has 6. Oxygen has 6, and I have 3 oxygens. So let's triple it to get 18. 5 plus 18 is 23. Which is an odd number, which should alert us to the fact that, hey, we have this negative charge here. That means we have an extra electron. So let's add another electron to give us 24. That's how many are in our picture, okay? So however many negative charges you have, that means you need to add electrons. If you had a positive charge, you would subtract an electron, okay? So let's put nitrogen in the middle with 3 oxygens around it. Let's connect them and fill up the octet of everything. Okay, let's see if we've used 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Ooh, there's too many here. So we need to get rid of those. But nitrogen needs an octet. So we're going to have to steal one of these electrons. It doesn't matter which one you pick from. And make it into a double bond. Okay, so if I'm going to make this look right, it doesn't matter which oxygen has the double bond, but whichever one has the double bond needs to only have 2 lone pairs around it after that, okay? Okay, and then because it's a polyatomic ion, we have to put brackets around it and put the charge on the outside like that. So now I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. So I've used my 24 electrons, and it looks like everything has an octet. So that's how I know I'm good. Now the thing I want to go back and go over is the molecular geometry. So for each of these examples I gave you, what if I was to ask you, hey, what's the molecular shape or the molecular geometry for each of these? Okay, so let's look at our first examples here. Now, I made this is in your notes. I'm not sure which page, but look back through our bonding unit, and you have this in your notes. Also upload a PDF of it. So this tells you, based on how many bond pairs and lone pairs you have, it'll tell you molecular shape. These are the molecular shapes you need to know for comps, okay? And this is, these are around the central atom, around the central atom, okay? So let's go ahead and figure out what the shape is for each of these. So this first one, here's my central atom. Let's count up how many bonds. 1, 2, 3, 4 bonds, okay? It has 4 bonds, and how many lone pairs around carbon? None. There are no lone pairs. This is a lone pair, but it's not around carbon. So I have 0 lone pairs. So that would be let's see, 4 bonds, 0 lone pairs, that's tetrahedral. Tetrahedral. Okay? The next one, let's look at it. How many bonds do I have around the central atom? I have 1, 2, 3 bonds around the central atom. Okay? And I have 0 lone pairs around the central atom. So 3 bonds, 0 lone pairs, that's trigonal planar. Okay, trigonal planar. Cool? Next one, I'm going to look at, okay, this was my correct structure. Cross that one out. All right, I have 2 double bonds. So what does that mean? If you remember back when we learned about this, a double bond counts as 1 bonding pair. So we're just going to count this as 1. We're going to count this as 2. So it's like I have 2 bonds and no lone pairs. So 2 bonding pairs, 0 lone pairs. Because a double bond is going to count as 1 bonding pair. So 2 bonding pairs, 0 lone pairs, that would be linear. Okay? Okay, let's look at our last 2 examples. This one has, look at your central atom, the one in the center. You've got 2 bonds, so 2 bonding pairs, and you have 2 lone pairs. Here's a lone pair, here's a lone pair. 2 lone pairs. So that would give you 2 bonding pairs, 2 lone pairs, that's bent. And the very last one, let's look at this one. Cross that one out. So I have 1, 2, 3. Remember, a double bond counts as just 1 bonding pair. So I have 3 bonding pairs, and I have 0 lone pairs around my central atom. So that would be trigonal planar. Okay? That would be trigonal planar. Now, the only other thing I might ask you, and you'll see this pop up as we get more into preparing for comps, which is what we're doing now, but maybe next week or the week after, I'm going to try to give you guys some more review materials, is I could ask you, hey, are these bonds considered polar or nonpolar? So not the overall molecule, but are the bonds themselves polar or nonpolar? And if you remember on the bonding lecture I did yesterday, it said that we're going for comps, just like pre-comps, we're going to assume that every bond is polar except for anything bonded to itself and carbon bonded to hydrogen. So if I said, hey, does this have polar bonds or not? You would say, hey, these are polar bonds. So these are polar bonds. Because the only things that are not polar, we're going to assume, are carbon bonded to hydrogen and anything bonded to itself. And because this doesn't fit within those parameters, we're going to call those bonds polar, okay? Same thing here. Okay, same thing here. We'd say, does this have polar bonds or not? Yes, this has polar bonds. And same with this one, okay? Because it's not carbon bonded to hydrogen or something bonded to itself, so this would also be polar bonds. Polar bonds, okay? Okay, and it'll be the same for the last 2 examples too. So the very last thing I want to do, what if I give you something like this? Okay, some crazy molecule, and I say, hey, what is the molecular geometry for these different areas that it's pointing to? So I'm going to look at this point here. So you're just looking at this atom right here, this nitrogen. So if you look at this nitrogen as the central atom, nitrogen has 1, 2, 3 bonds around it and 1 lone pair. So 3 bonds and 1 lone pair, that would be trigonal pyramidal, right? So I would say trigonal pyramidal. I'm going to abbreviate. Okay, this one I'm going to look at carbon. This is my central. It has 1, 2, 3, because remember double bond just counts as 1. So it's 3 bonds, no lone pairs. 3 bonds, 0 lone pairs, trigonal planar. So let's say that's trigonal planar. Okay, this one, as my central atom, it has 2 bonds, 2 lone pairs. If I have 2 bonds and 2 lone pairs, that's bent. And this one has 1, 2, 3, 4 bonds and no lone pairs. That's tetrahedral. And this guy right here, this has a bond, a triple bond. Triple bonds and double bonds both just count as 1. So this is like it has 2 bonding pairs and 0 lone pairs. So if I have 2 bonding pairs, 0 lone pairs, that's considered linear. Okay, that's how you would do a question like that if that were to show up on comps. All right, go ahead and do the assignment, guys. Good luck.